Hey there. So there's a lot of talk on the internet today around marketing mix modeling and MTA. So if you are in the marketing or analytics space, you must have come across these sort of debates. Um, MMM vendors, MTA vendors having a go at each other, or other consultants and experts and marketing practitioners. Everyone basically having a say on this. And while this is very healthy, all this debate, but it's also important to really have a clear idea about what the real differences are and what advantages really are in each method. And I definitely take sides with MMM much more, because first of all, the conversion tracking itself has so many possible loopholes and lapses today in MTA. And then on the other hand, in MTA, in most cases, it's so difficult to really build a good multi-touch attribution model, because again, the data itself is so dubious. So one of the biggest advantages of MMM, which actually is missed by even those people who criticize both MMM and MTA, or even just criticize MTA, it's actually the advantage of having a scientifically robust budget allocation method. Allocating budget optimally is one of the biggest pluses and biggest strengths and merits of MMM, I would argue. So that's what I'm going to show here, how actually this budget optimization process is done in MMMs. So you'll see that it starts with this, that this old thought process where you're just pitting MMM against MTA only on the points of modeling and statistical modeling, or the quality of data. It's actually overlooking the most important aspect of MMM, which is the power of really of answering the question, where should I be placing my next dollar, instead of just talking about where to give credit. That's not its biggest strength. I mean, that of course is a strong point as well over MTA, but the biggest strength really lies in answering the question about where to put the next dollar. And that's where the real it's not really a secret, but the real advantage of MMMs lies in the saturation curves. Once you've determined saturation curves correctly, of course you have to get it right. The mathematics of it has to be right and suitable and apt for that particular data set and that particular brand in question. But once you get it right, it actually helps you determine everything, like at what point you are really profitable, at what point you stop being profitable, and how you can really optimally reallocate the budget. And there are two types of saturation curves that I will talk about here, and again, there are so many other kinds as well, but typically the one on the right hand side, hill saturation, this is the most generic form. X this form here, which has alpha in the power, and you have two parameters essentially, x and k. So the point here is that if you are going to do um I'm sorry, there are two parameters here, alpha and k. And the point is, if you are going to use hill saturation, you should have a good reason for it. But you can basically split this up into two cases, where alpha, the one in the power, this is less than equal to 1, in which case it actually becomes concave. And in that case, you can actually use convex optimization. Okay. So that's where algorithms like CVXPY, or other code bases like CVXPY, can be used. That sort of packages or libraries. Whereas alpha greater than 1 becomes essentially S curve. And this, and again, I'm talking about the hill saturation curve here. And then you have to use more advanced libraries like NLOpt or IPOpt. And there is a problem there, because there's an inflection, as you can understand. This means that this just changes direction, and you also have multiple points where, which can be called as local maxima or local highs. So therefore, local optimum is probably your best solution. You might want to really optimize and try to get better solutions. But on the other hand, if you actually have a concave curve like this, which is guaranteed concavity, for instance, exponential is one. In that case, in such a response curves case, which takes this form, of course, then you have a global optimal, which is guaranteed, and it's much faster. You can always use CVXPY. So this is just to give you an idea of the kind of mathematical stuff that actually goes on behind the scenes. And again, just to give you a quick idea, just like I said, the global optimum is always there, and there's only one of them in case of a concave function. And therefore you can use CVXPY which is basically a package which is used specifically, a Python package which is used specifically for convex optimization. And this is the case of convex optimization when your curve is concave, whereas in S curve, it is it is non-convex, but it's also not necessarily concave either. So it can have different kinds of, um, depending on the value of alpha, it can have different shapes. So this mathematical proof, for those who are mathematically inclined, you can check for concavity by taking a second order differential. So that's what has been done, and if that becomes less than 0, then it actually becomes concave, and then that's when you use CVXPY, and you have a global optimum. Whereas when the alpha is greater than 1, this changes sign, has an inflection point, and therefore you cannot have guaranteed concavity, and you need a tool, a Python tool. Essentially, it's a package. You have to use NLOpt, which is the algorithm. It's not a package, it's really an algorithm, and you will have to use that, and you can probably best hope for local optimal and local optimal solutions. So again, now the next question really is, how many variables that you really need. And in terms of number of variables, you really have to look at two or three things depending on how you have set up your modeling. If you have only, if there are no geos, if you have only like number of channels and days, so number of days into number of channels essentially becomes your number of variables, which is what has been given here. So a single channel, for 30 days will have 30 variables. If you have three channels, 365, so you have just multiplied these two, and so on and so forth. If you have more constraints, then you will also have to consider those as well. And you might also have multiple geos, so you have to consider those as well, and then that becomes another multiplying factor. So the whole point is to actually get a good solver. Now we were talking about the mathematical part so far, but then there's also the question of uh, you know using the right kind of code, right? The right kind of optimizer. So you cannot actually have solvers. If you have used Excel, you know that there are actually solvers within that also, but you really can't use those for the kind of real life problems that you will actually come across, because Excel is going to crash. So if you look at speed and accuracy, I'm actually going to skip this, but for those who are more technically inclined and who want to also improve the performance, like that's actually a next level thing. But if you want to increase performance also, and you can then see which one among these is the best. Okay, but you also have to look at which one is ideal in which case, apart from that, apart from the speed as well. So like I said, when it's concave, you can actually use both exponential and hill. I'm sorry, when it's exponential, it's always concave, and when it's hill, it's actually concave. And I mean, when it's concave, when you're using hill, it's you can use CVXPY. But when it's more S curve, because the alpha is greater than 1, then you have to use NLOpt. And like I said, within NLOpt, it's an algorithm. There are several sub algorithms as well. So you can also use SCIPY. So I'm going to talk about two packages here: SCIPY minimum, SCIPY optimize minimum, minimize rather. That's what I'm going to use here, and I'm also going to show you CVXPY. But you can obviously try out NLOpt as well, and probably I make in the future videos as well. So the CVXPY is actually very fast. That's its advantage. Like it's extremely fast. I've also run this, and unlike many solvers which actually takes several minutes, and depending on the complexity and the depth of data, it can take a very long time. But CVXPY, when possible, again, to apply, it is only possible when it's a convex optimization problem, like I said, a concave case, then only it's possible. And in most cases, if you are in the digital space, concave is what you're going to get. To be honest, you're not going to get convex very often, or other shape. So you can actually, and again, remember, the saturation curve determines what kind of optimizer you can actually use. The case so here there's a case study. I'm actually going to just skip that one. Yeah, so this is just the how you can basically decide when when it is actually optimal and when it is not. So this is basically what happens after optimization, which is not very difficult. There is another mathematical principle which just says that in the marginal, the concept of the saturation curve is that, there's always, you're trying to basically get to a point. The optimal point is basically when the marginal ROAS is actually the same. So this is what is a marginal ROAS, as you can see, of all the channels, and that is equivalent to a Lagrange multiplier, as it's called. So that's basically the concept of the saturation curve, basically of diminishing returns. But I will, so in plain English, this translates into the last dollar spent on Google should generate the same incremental revenue as the last dollar on Meta or TikTok. Okay, that is the most optimal allocation of budget, essentially. Now the implementation checklist, like I have said, fitting your mmm, of course, that's your first point. Then you have to start, with your curve shape. Then you have to set up your optimization, then you have to run your solver, and then actually do the implementation bit. So I will quickly jump now into the the data and the analysis part of it. So this is data which is taken from a from a data set which exists online, and after that data set has been taken, this is what basically gives you sales and also the media columns. Okay, and it you don't actually have any intercept, by the way. And this is how the data set has been built. And remember, we are not doing the entire mmm here. So what we are doing is, we are just assuming that the mmm was done, and from there we actually had these static parameter values. Okay, so just imagine that we had the coefficient for television, the carryover, saturation, all the coefficients basically for the media channels that were, we are assuming that we already have them from the mmm analysis. Then we construct the carryover matrices, which is, remember, we just said that we're going to, yeah, so basically we are creating the carryover matrices. This is what how it's going to give us our ad stock, and then we are going to use them together with the saturation curve as well. So this is how we construct the sales variable, which is our outcome variable, which includes both. This basically is, as you can see, the exponential formula here. So we are taking saturation and carryover together and constructing our variable, sales variable, and on the basis of that, this is the prediction. So we have a massive difference. As you can see, this was the actual sales data. Remember, we had loaded already the sales data, but in this case you'll see that we have the predicted sales, and then there's a difference, and then there's a huge percentage difference. This is basically your MAP. So naturally, what was required here was actually an optimization problem within all this optimization problem that I'm showing you for budget allocation. This optimization is for finding the optimized parameters. Remember, we had started with a set of parameters, but what we are now going to do is we're going to try to find out the more optimized set of parameters. So there's a whole bunch of code here. I'm not going to walk through the code, of course, entirely, but you can just take a look at how this has been done in a very similar manner. Again, you're just calculating the different contributions in this fashion, and that is nothing but simply, that you're just basically multiplying the coefficient with the transformation that you have done on the media variable, right? So that's how, as you can see, this is the coefficient, and then this is the transformation that we were talking about, right? And then you obviously have your initial parameters, and then within certain bounds we are actually optimizing it. As you can see, this is the kind of optimization that has been done here. And then the optimal parameters are found out, and on the basis of that, the MAPE this time becomes much lesser, like from 80% is jumped down to 12.19%, right? And then, as you can see, it's far closer this time to the actual data than previously. And this is just a plot now of the actuals versus the predicted. As you can see, fairly good prediction even without the intercept. And now this is the contribution by the channel. This is the code for the contribution by channel for each channel. Once again, this time we have actually calculated the different contributions, the absolute numbers this time. Okay, And then you have the goodness of fit, where you can get the R square, the map we got previously as well. And yeah, so this is basically done in using two this is does done using sklearn as well. So just two approaches, you have almost got the identical data here. Now is the, finally, so up till this point you have to do, right? Of course, R squared and all, you might not necessarily do, I mean, but you would have done that anyway through MMM. What is important now is, after you've got your saturation curve, you've got your contribution charts, you've got your saturation curve, now what you need to do is run the CVXPY. So this import CVXPY as CP. You then extract its optimized parameters um, of the model. So we are going to go through that process again here quickly, just to build our um, our contribution, and we are declaring our CVXPY variables, and then we define our constraints. So remember, an optimization problem has an objective function. So basically you're maximizing or minimizing a function, a mathematical function, and you have, that's going to happen subject to some constraints. So there's going to be some constraints, so you have to define it like, each of the channels will be non-negative, right? So they will be greater than or equal to zero, the spends, that is. And then the sum of these will have to be less than or equal to the original total spend. So that becomes your bound of total maximum total budget. So that defines your objective function, which simply is nothing but maximization of the same sales function that we had. So that sales function is the contribution, sum of the contribution of the different channels. And then you just solve it, right? So as you can see, there's not much here. The rest is just printing out different things. And once this has been done, you actually get the summary format, which tells you, this is your optimal total sales, this is optimized total budget, and this was your total budget. So the total budget and optimized budget will remain the same, of course, but what is going to change, by the way, this is not necessarily going to remain the same. This can be lesser also, but it has used up the total budget, because it was possible to do so profitably. As you can see that in the sales improvement, the reallocation, you can see, by the way, this is the spend per channel, and this is a reallocation. This is the new budget that that it has suggested, and this is the original one. And you can see the original one is, in this case it's lesser. In the third case, in case of banners, in case of TV it's lesser, in case of banners it's much more, in case of radio it's nearly reduced it to zero. Again, this is of course based on dummy data, and this did not even use an intercept. So you will probably have to do a more complex modeling just to find out if this even makes sense, because according to this, radio is completely useless and you should not be investing money in that. And it's not profitable, so you should take money out of it and reinvest in the other channels. Now we're going to do the same thing with SciPy minimize, and within that, the sub algorithm SLSQP. And like I said before, this is suitable if you are, if you are actually using a concave method or convex method. So this is fairly useful for a wide variety of methods. And once you have the same construction, the construction is very similar, as you can see: carryover effects and saturation effects. And once you have built that, you have created the objective function, you've got the constraints, and then finally you solve for the, you solve the optimization problem, and then you display the results. And this is what you get. This is the sales improvement. It has an improvement of 4.88%. So comparatively, the difference, if you look at with CVXPY did actually much better, because it had more optimized sales, as you can see, right? So CVXPY was able to find out more optimal solution. Now you can just compare these budget allocation methods, and this gives you a nice overview of the comparison of the allocation methods. You will see that, how the budget has actually been reallocated by these two models, these two algorithms. As I said, for CVXPY, you can see radio has been completely removed, right? That's why you don't even have the orange here. And you will see the total sales by method, both are more than the original. So both have been able to find, have been an improvement over the original one. So you can actually get more sales than what you have if you just reallocate the budget accordingly. but CVXPY is suggesting a method which at least in theory is going to give you a better return. And you can actually have the channel wise spin comparison, which is basically another way of putting the same thing here. The previous one was stacked, and this one is grouped. And you have sales improvement versus original, where you have CVXPY and you have the SLSQP, which have been compared once again. So the sales improvement, like I said, is actually higher in case of CVXPY, which is almost 17%. So this is just a table that gives you the how much has been suggested, what is the difference. That detailed comparison has been given in the form of a table. So this was basically budget allocation methods using I've shown you two methods. Again, I've also talked about the flow again. Remember, is simply that you can do uh you're going to basically run the you're going to do the saturation curve, you're going to have the ad stocks and everything. But it's the saturation curve that's the key transformation that determines the shape of the curve, and therefore from there you can decide whether or not to use a particular kind family of algorithms. Just to give you a brief understanding again, I've also talked about the different the kind of constraints that are there for CVXPY as well as for SciPy. So in SciPy optimize minimize, you only have like three round constraints and one equality constraint. Okay, whereas in case of CVXPY you actually have like I said, the number of periods into the number of multiplied by the number of channels. So there are 600 variables actually, and therefore one more basically that makes it the total then becomes 601. So CVXPY has a lot more to deal with, but it still manages to actually run faster. So that is the overall description of the process. If you have any more questions about this workflow, any more questions about other libraries, I will be, like I said, probably doing videos on NLOpt as well in the near future for budget allocation. But if you need more information on this, do let me know in the comments. But hopefully this was useful, and if you've liked this, do like, share, and subscribe. And I'll see you in the next one.